Hi, and welcome to week 1 of Managerial Statistics. This is our intro chapter. We actually start on chapter 2. That's the good news. We're already 2 chapters in. You did not miss chapter 1. We're just not going to cover it. It's not necessary. My name is Matteo DeMuro, and I am your instructor for this course. I have never taught a course like this before, so I'll be kind of learning with you guys, and I'll be hoping to get your feedback on what works and what doesn't work. So if you want to follow along in your book, you kind of can. I sort of modify examples or make up new ones to sort of supplement your textbook, and all my materials are on Moodle. So I actually have a note package that you can download and print, and I suggest that you follow along using the note package and use that as you watch this video. Make use of the pause button. You can go back and re-listen to things, and I will also be posting some small little tutorial videos for specific examples as well as the ones we're doing in the notes. So what are we doing in this chapter? Well, there are a lot of topics in this chapter. This is going to be sort of a big video. None of the topics in and of themselves are ginormous, but there are a lot of them. So you can see from 2.1 to 2.9, these are the things we're going to cover. We're actually, 2.9 is optional, so I'm not really going to cover it. It's not going to show up on any tests or anything like that. But we're basically looking at the introductions to, how we sort through data, things that we call a distribution in 2.1. 2.2, we're looking at central tendency. That's just a fancy way to say average. And measures of variation is just basically standard deviation, things like that. 2.4 are percentiles, quartiles, box and whisker plots. Those are all ways of visualizing data. And then we're going to be looking at some descriptive, qualitative data kind of stuff. And we're going to wrap up with scatter plots, which also helps us visualize data. And then in 2.7, we're going to see some misleading graphs and charts, kind of the standard things that, they like to show in statistics. Look at this chart. It doesn't look good. It's misleading. So that's 2.7. And, now that I'm looking at it, 2.8 and 2.9 are sort of optional. So we'll see as we progress through the course if we're going to do anything with those. So starting off right away with the shape of a distribution. So the population, when I say the word population, I'm going to be referring to the thing we're studying is the population. So whether we're looking at, basketball players or, how many trips to the grocery store an average person makes in a month, our population in that case would be, everybody who goes to the grocery store. So when we have a population of things or data, we like to know what's the shape of that distribution. So if you graph it out, does it have any specific kind of shape? And it turns out that a lot of distributions do have particular shapes. And some ways that we sort of graphically look at them are, stem and leaf displays, frequency distribution, something called a histogram, and then the good old dot plot. So we'll be looking at some of those. Let's look at the stem and leaf display first. So the purpose of a stem and leaf display is to see the overall pattern of the data by grouping it into classes. So we sort of group the data using a specific method, and when we do that and then we graph it out, we can sort of see variation from class to class. We can see how much data is in a class, and then that kind of gives us an idea of the distribution of the data within each class. So this obviously isn't going to work super well unless you're using software. If you have like 1 million data points, that's going to be hard. So this is best for sort of small to moderately sized data distributions. This is an important slide. You're going to want to, mark this one, put a star on it, put a sticky note on it. So when you're making a stem and leaf display, you might also want to pause the video here and just read through this on your own, but there's basically 4 steps that we're going to do, and I'm just going to quickly summarize them. So you're going to want to sort of figure out who's going to be your stems and who's going to be your leaves. Now that'll make more sense when we actually look at some numbers in the example that's coming up. Basically, if you have a number like 10 or 12 or 13, your stem might be the 1 for the 10, and then your leaf might be the 1's digit. Okay, so that's what I mean by stem and leaf. And basically, you should organize them from smallest to largest. And then you're going to be entering the leaf for each measurement into a row. And if you want, you can also rearrange your leaves so that they're increasing from left to right. So I think this is best demonstrated by just looking at an example here. So our example is, and I just made this one up, it's the number of minutes that cell phone users use their phones to talk were recorded by a company. And then we have all the minutes there. So the question says, complete a stem and leaf plot summarizing the data. And I'm just going to remind you there that it is important to organize that data from smallest to largest. So if you go to the next slide here, this is probably the easiest way to organize. Now I am going to go ahead and grab my pen here. There we go. So over here, we're going to just maybe recopy our data from smallest to largest. So I recommend that you go back to this page, have it open so you can see it. And just what I like to do is I just like to scan through and say, okay, well, there's the 2, and I'm just going to write 2, and then I'll go back and scan through and say, okay, there's the 9, and cross it off and go 9. So I'm going to go do that. You should pause the video and try it out on your own. Something to note, if you do have a duplicate number, like there are 2 22s in here, so there's a 22 and there's a 22, you just write that number as many times as it comes up. Now I'm going to run out of room, so I'm going to keep going over here underneath. Now there are 2 41s, there's a 45, a 60, 71, 74, and I'm just running out of room here. There we go. Okay, so you got your data written out from least to greatest. Now that's really going to help you figure out your stem unit and your leaf unit, and you'll see what I mean in a second. So when you make this table, over here I'd write frequency. Okay, so frequency is just how many times does a certain number or group of numbers come up. Then in the next column, go ahead and write stem, and then over here write leaf. Now, what is the stem and what is the leaf? Well, I'm looking at my numbers, and the biggest number I have is a 2-digit number. So if I'm just going to pick on the number 75 here for a second, I'm going to be referring to that digit as the stem and that digit as the leaf. Okay, so the stem is the tens digit and the leaf is the ones digit. That's something that you'll have to decide for yourself when you're doing a question. Okay, because obviously if you have 3-digit numbers, you might do it differently. Okay, and then you can see the homework for more examples on how to do that. So I'm seeing numbers like 2 and 9 that don't have a tens digit, so that would make the stem a 0. Okay, and then in this column we write all the leaves. Okay, so we have a 0, 2, right, as in nothing for the tens, and then a 2 for the ones, and then we have a 0, 9. So there we go. So I got 2 leaves. So the frequency in that category is 2. There's 2 pieces of data in that category. Now, if I look at the next kind of grouping of data, I see, well, I got some numbers that are in the tens, right? I got 11 and 14. So I'm going to go ahead and write a stem of 1. So as in like 10. And then I have 11 and I have 14. So I just write those there. And I can see that I got 2 in that class there. The next one are the 2s, right? I got 21, 22, 22 again, and then 29. So I got a stem of 2, and then I got 21. So I write a 1. I got 22, so I write a 2. I got 22 again, so I write another 2, and then I got a 9. So in this class, I got 4 pieces of data. So I'm going to write a 4 in the frequency. I don't have a stem of 3, but I'm just to make the table complete, I am going to put that, and then you just leave that underneath leaf, leave it empty because I don't have anything that has a 3. So frequency is 0. I do have a stem of 4, and I got 41. I got 41 again, and then I got 45, and that's it. So that has a frequency of 3, and I don't have a stem of 5. So once again, that's going to be leaving the leaves empty and put a 0 under frequency. I do have a stem of 6 because I have 60. I'm going to put a 0 there. That one has a frequency of 1 in that class. And then I do have some that have a 7 here. So I got 71. So put a 1 in the leaf column. I got 74, 75, and 76. So now that has 4. All right. So now that you have this pretty little data table, you're going to be able to make something that's called a histogram. So as far as this example goes, this is it. So we've now made a stem and leaf plot. And how does this help us visualize the data? Well, we can actually see the frequency over here in each class, right? So I'll just highlight that, right? We can see the frequency here. So I can say, okay, there was more numbers that had a 7, starting with a 7, than there were, say, than starting with a 5. There were no numbers starting with a 5. And I can see that, for example, my biggest categories were this one and this one, right? So numbers that started with a 2 that had a stem of 2, there was 4 of them, and then numbers that started with a stem of 7, there was 4 of them. Yeah, so that kind of helps you figure out where, you remember, these were cell phone minutes, right? How long do people speak on cell phones in a month? So seems like mostly people are speaking, not very much, 20 minutes a month, or, somewhere in the 70s. Right on. Okay. So what is a frequency distribution, also called a histogram? Frequency distribution is a list of data classes with the count of values that belong to each class. So you can kind of think of it as a classify and count kind of thing. The frequency distribution is a table, so kind of like the stem and leaf plot, but not really. We can show frequency distribution in a histogram. So a histogram is just a picture. So it's just a graph, and we're going to actually make one. Now, there are about 5 steps to making a histogram. Okay, so I recommend you pause here and you review them. It's not going to mean a lot right now, like what each step is, right? It's going to, find the number of classes K. Like, what the heck is that? Find the class length. Like, reading this list right now doesn't really help me, but once you know how to do one, this list will guide you. You need to do each of these steps to properly do a histogram. Histograms have a lot of steps in doing them, okay? So it's very important that you sort of keep your eyes on the prize and make sure you're doing all these steps. So we're going to switch to a different set of data. Now this one is a sample of payment times. So just how many days I believe it took, say, a client or something to pay an invoice that a business sends them. So each box is a different data point. So you got 22 days, 29, 16, blah, blah, blah. One thing you're going to have to do in this question right away is you need to figure out how many pieces of data are there. And we're going to use the letter N for now to do that. Now, this is a table that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 by 1, 2, 3, 4, 5, 6. So there are 11 times 6, 66 cells, but the last one's empty. So there are 65 pieces of data. So I'm just going to write 65 data. Okay, that is great. So step 1 is the number of classes. So group all of the N data into K number of classes. Now that's kind of some like math jargon, but it's very important that you follow this formula here. So basically what we're trying to do, let me show you the end result. Oh, right. I have to draw it out. My bad. I was going to show you the end result, but the end result is going to be sort of this table or this drawing that sort of looks like this. It's going to kind of look like this. We'll have some numbers here and some numbers here, and then it's going to look something like that. So we're making each bar here in this graph is sort of one group of the data. Okay, so what we need to do is we need to decide, well, how many different groups are we going to have to make a nice histogram? So what this formula here helps us do is figure out how many classes we need, and we always use the letter K to just talk about K is the number of classes. Now, when you take 2 and you raise it to the power of K, it has to be greater than or equal to N. Now remember, in our example, N was 65, so there was 65 pieces of data. So you essentially do a little bit of guess and check to figure out what K should be. So down here, if you look right down here, says if K is 6, well, 2 to the power of 6 is 64, okay? And that's less than N. Right now, our N was 65. 64 is not bigger than 65, so a K value of 6 would not work. It would not satisfy our little equation here. If k was 7, so that's 2 to the 7, you get 128, and that is bigger than 65, and that's as close as we're going to get. So we're going to be using k equals 7. Now, some of you might say, well, how do I know? You're literally guessing and checking. So if you weren't sure, you might start with 2 to the power of 2 and say, well, that's 4. 4 is not bigger than 65. Might try 2 to the 3. Well, that's 8. That's not bigger than 65. So eventually you're going to home in on what it is. Some of you will be faster than others. That's okay. But we're going to be using k equals 7. Now, just to be super clear, you must use this formula. Okay? So you will have a formula sheet in this class, and I do have some of these formulas on there. That's the formula you got to use. So that's step 1. Number of classes, done. Now, the class length. What is the class length? Well, the class length is the step size from one class to the next. So basically, how are we going to know which data fits into class 1 and class 2 and class 3? Well, there's a formula for that as well. And here it is. So L for length is going to be your largest measurement in your data set minus the smallest measurement divided by the number of classes k. Okay, so for our example, if you go back to the table, now this does take some searching, but 29, I promise you, is the biggest number in our data set. And to establish that, you'd have to scan through and make sure that it is. Okay, so it is in this case. And if you scan through likewise, the lowest number is going to be 10. So if there's more than one 10, it doesn't matter. Is there more than one 10? It doesn't matter if a data repeats itself. It's just what's the highest and what's the lowest. Okay, so what we're doing then is the highest measurement, 29, subtract the lowest one, 10, divided by the number we figured out in step 1, which is 7. Okay, now when you go 29 minus 10, you get 19, and then 19 divided by 7 gives you 2.7143. Well, that's a really ugly number. So the way that everybody agreed to do this is you're going to arbitrarily round your class length up to 3. Okay, and we always do that. So if I got 2.1, I'd be rounding up to 3. Okay, this is the minimum class length. Okay, it must be rounded up every time. Now, the class widths. This is just going to help you sort of organize your data a little bit here. Okay, so the classes start on the smallest data value. Okay, now we already established that that was 10. Okay, in the last step, we just determined the length of each class was 3, so 3 days. So class 1 is starting on 10 and then add 3, and notice the language here, it's 10 days to less than 13. Okay, class 2 starts on 13, so actually includes 13, and then you add 3 to go less than 16. Okay, take a moment and see if you can actually fill out the other class lengths. Okay, so class 3, for example, is going to start on 16 to less than 19. Now I'm using the symbol for less than, so hopefully that doesn't confuse anyone. Class 4 is going to start on 19, and it's going to go to less than 19 plus 3 is 22. Class 5 is going to actually start on 22 and go to less than 22 plus 3 is 25. Class 6 starts on 25, and it's going to go to less than 28, just add 3. And then the last class starts on 28 and goes to less than 28 plus 3, 31. Now, if you did this right, your very last class should be your outside number here, this 31, should be bigger than your biggest data point. Remember, the biggest data point was 29. Okay? So there it is. You've made a nice little table to help you organize your data so that eventually we can make a histogram. Now, remember, why are there 7 classes? That's because in step 1, we figured out that k was equal to 7. So what we've done is basically we figured out a nice way to have a good number of classes so that the data is sort of evenly distributed. And we figured out how big each class should be so that it's not like skewed on one side, right? So every class is kind of nicely distributed with a length of 3. Okay? We're almost there. All right? Now you're going to make a table that just has your classes in it. Okay? So that's this right here. is what we just did. Okay, the frequency, so how many data points are in that class of data points that start on 10 and go to less than 13. So not actually including 13, basically in our case, 10, 11, 12. Okay, so how many 10, 11, 12s are there in our data set? Now, I've started filling it out over here with the relative frequency. Relative frequency is just when you take the frequency and you divide by the total number of data points. So we got 65 data points, and you go 3 divided by 65, you get 0.0462, or 4.6% of the data is in this class of 10 to less than 13. Okay, you're going to have to go through that wonderful data table, it's going to be your best friend, and literally count all the data points. Okay, so for 10 to 13, now I've already highlighted some. I don't know if I can erase that. Oh, I can erase the highlighter. Yay! Totally prepared. So, 10 to less than 13. So scanning through, I like to start here. I'm going to go through. I got 1. Remember, 13 is not included, right? To less than 13. So not including 13. So there's 1 data point, 2 data points. There's a 14. Just scanning through each row. There's another 13, which is too big. Where is that last pesky data point? It's in there somewhere. I missed it. I gotta go back. Ah, there it is. Perfect. Okay, so it does help if you cross them off or highlight. So that's why I wrote the number 3 here. Now for 13 to less than 16, there are 14. So I suggest that you pause the video, pause it, go and find them, count them up, and cross them off. Okay, pause the video right now. Do it. Give you a moment. Okay, so you should have found that there's 14. Go 14 divided by 65, you get that relative frequency. Likewise, you're going to have 23 and 12 for the next 2 classes. Okay, I'm going to finish filling this out. I do recommend that you go and try it out yourself. So there are 8 in this class, and there are 4 in this class, and 1 in that class. Now, the relative frequencies don't necessarily show up on the histogram, okay? But I'm just going to do the fraction. So 23 divided by 65, 12 divided by 65, 8 divided by 65. You get the idea. Sometimes it might ask you questions about that, sometimes it might not. All right, now we can actually go ahead and draw our histogram. Now this is way easier to do on the board. I got this ugly click to add text right here, so give me a moment. I thought I got rid of all these things. I'll have to edit this out. All right, great. So I'm now going to go ahead and make my very pretty chart. I'm going to use a bit of a thicker pen. So I'm going to do my best. Now, I got 2 sort of things here. I got frequency histogram and percent frequency histogram. I'm just going to do one because they're basically the same thing, but I'll tell you how to do the other one. It's just one extra sort of thing. So you're going to need to use a ruler. Now, I'm doing this freehand on my computer, so I am not using a ruler. So I'm going to do my best here. And that is pretty good. I'm very proud of that. Now, you need to make sure you're labeling your axes. So remember, this was a payment time question, right? So down here, you can write payment time. Don't forget the units. You will lose marks if you don't have the units. Over here, you can write frequency. Now, our data points kind of range from anywhere between 0 and 30, basically, right? If you go back and look, 10 was our lowest, 29 was our highest, but usually you want to start on 0 and work your way up to your biggest data points. So, 10 to 29, I'm going to go up by 5s. So there's 0, 5, 10, 15, 20, 25, 30. Now, you do need to label. There. And down on the horizontal axis, remember horizontal is like the horizon, so this one down here, payment time. This is where we use our classes. Okay, so we got 10 to 13, 13 to 16, 16 to 19. So what I'm going to do is, I'm going to sort of leave a little bit of space from the 0. I'm going to go over here, and I'm just going to make a little tick mark and write 10. Okay, it is 10 to 13. Right? Each class goes up by 3. So each tick mark here is going up by 3. So this will be 16, this will be 19, and then we had 22, 25, 28, 31. Now I'm going to switch colors. I'm going to go with a nice classic color here. So in our first class, looking at our table, in the class that was 10 to less than 13, we had 3. So what I'm going to do is I'm going to make something like this. There. And as a nice courtesy, if you can write above it how many are supposed to be in there, that really, really helps. Okay, so what am I looking for when I'm looking at this on an assignment or something is, that you're less than 5. And hopefully past the halfway point, okay? The next class, the 13 to less than 16 was 14. Okay, so there's 15. So I just want to be just below it. I'm going to do my best. My finger on my screen sort of gets in my way. So you're drawing a bar and you write 14. Now, it might be debatable if I'm actually kind of at the 15 mark there. Again, I'm using my finger on my computer screen, so I'm having some issues, but when you're using pencil and paper, it is a lot easier. Now, 16 to 19, that class had 23, so I'm going to do my best to sort of go below 25. Boom. Not bad at all. Make sure you write the number above it, and that really does help. Now, the next class, looking at that table, was 12. So there's the 15. Again, I'm not going to be super crazy, but you better be sort of far away from the 15. 22 to 25, that class had 8. So there's the 10. I'm going to go a little bit lower there. And there's 8. I cannot, for the life of me, make a nice 8. They are hideous. The class 25 to 28 had 4. So here we go. Now that's a questionable 4, but there it is. And then we had 1 like that in the last class. There. So this is a frequency histogram. What's the deal with the percent frequency histogram? Well, that's why our table had these relative frequencies or percentages. Okay, so the only difference between the frequency histogram that we did, so that's the one we did, versus this one here, is that instead of the numbers, so instead of writing how many there were in each group, you would write the percentage above. That's it. It's the only difference. So I will do 1. So for example, in our first class, it was 4.62. So if this was the percent, I would have written 4.62% instead of the 3. There you have it. There's your histogram. Absolutely stunning. All right. I just want to make sure I'm still recording here. Yep. Anytime. Good. We're still recording. Beautiful. Okay. So, now we're going to talk a little bit about interpreting data pictures, something called skewness. So, there are 3 different kinds of skews that we like to talk about, our favorite skews. Let's start with symmetrical. So if you start graphing data and it starts to look like the good old bell curve, that's a symmetrical distribution. There you have it, also called the bell curve. Now, positively skewed, one too many skeweds there, but positively skewed is when you sort of see the hump sort of on the left-hand side, okay? So what we talk about here when it's positively skewed is the right tail of the histogram is longer than the left tail. So if you look over here, this is called the tail, and the right side of the tail is sort of longer than the left-hand side. So sometimes this is called right skewed, and over here negatively skewed. Sometimes this is called left skewed because the tail is over here to the left. Okay? Yeah, we actually do end up talking about that quite a bit later in the course. Here is a stem and leaf display. Stem and leaf displays and dot plots are useful for detecting outliers. So what is an outlier? Well, they're unusually large or small observations that are well separated from the remaining observations. How we deal with them when we do our data crunching, or even when we are making our diagrams and things like that, it's kind of dependent on why the outlier is there. This is just a number line, but each value is represented by a dot that's placed above the corresponding scale value. And you can kind of see most of this data is sort of over here and in the middle. Okay. And then you have, sort of over here, this one, like 32, whatever it happens to be. That's clearly an outlier, right? Like most of our data is kind of ranging from, the 60 to just shy of 100 range. Okay, there are ways to calculate and detect what an outlier is, different thresholds, and we'll sort of look at that in another example. Just kind of going through the lingo right now. Population parameters. So it's that fancy word again. A measure of central tendency represents the center or middle of the data. It's an average. Okay, central tendency is just the average. People talk about the average all the time. What is a population parameter? Well, a number calculated from all the population measurements that describe some aspect of the population. So if you start talking about average height of basketball players, that's a population parameter for basketball players, right? Like what is the average height in the NBA? What is the average height on basketball high school teams? Okay, those are all maybe going to be different. A sample statistic is a number calculated using the sample measurements that describe some aspect of a sample. So obviously it might be hard to measure the average height of everybody in Canada. Okay, so what we do is we take a sample, take some measurements in BC, all the different provinces maybe, and we say, okay, so the average height in Canada is this. Okay, so it's just a sample. All right. What are the symbols we use for measures of central tendency, right? AKA the average. Well, there's a couple of them. The mean, or what most people refer to as the average, is this. It's a U looking thing, and it's pronounced mu. I think it's a Greek letter. Mu. It's kind of like a bad cat. Mew. Doesn't quite sound like a cat. It's a weird cat. So there it is. Kind of go like that. There it is. The median is usually, well, there's different ones, but we're going to use a big M with a little d, little subscript d. So median. And then the mode is a big M with a little O. You'll just have to sort of remember those. It's kind of annoying. What is the formula for the sample mean? So again, you have a formula sheet, but it is good to know these sort of by heart. Now, this is going to look really fancy. If you haven't taken a math class in a while, there are a few things here that might be sort of jogging some bad memories for some of you. So this is the symbol we use for a sample, is X bar. That's how it's pronounced. So right there, that is called X bar. You'll get the lingo. And we use it for a sample. If it's a population, so if we're talking about the true population, then we use mu. But if we're just doing a sample, we took the average height of everybody in the class, then we'd use X bar. Now, this here, this stuff here we'll talk about in a second. That's the fancy way to write the formula. But basically, everybody knows how to do an average, right? You take all your measurements, x1 plus x2 plus ... until you get to the last one, right? So you add up all your measurements and then you divide by the total number of measurements and you got your average. Okay, now we are going to be using a lot of formulas in this class. So just to start introducing you to some of the symbols that are here, this E looking thing is called epsilon. It's another Greek symbol. We love Greek symbols. It's epsilon, and what this means is the sum. So it's do the sum. Do the sum of what? Do the sum of every xi, so every data point, starting on I equal 1, so starting on your first data point and continuing until you get to n, as in the last one. You will get used to that lingo, but that's what that means mathematically. When I see that, I know it means all those things. Okay, so it says do the sum of every xi, starting on the first one, going to n. and then divide it by the total number of measurements n. I recommend that I got this important thing that you write that out down there. Now I can maybe go and insert a text box. Yes, I can. I will make it look so hard. I got it. Thanks a lot, Microsoft. Oh no, there we go. My text will go there. So, no, there we go. So I can't do that symbol, so I'll have to leave some space. Now this is supposed to be an I. Now I'll switch back to this and I will just doing that epsilon thing. There. So just so it's in your notes, the sum of every xi, so this thing here, that epsilon thing, just means add every data point starting on I equal 1 on x until you get to n, the last data point. There you have it. So, whew, boy. We'll get better and better at this. So here's a really quick example of calculating the mean. So it says the sample mean for the hourly wages for five vocational areas in business and finance, nature and sciences, health, occupations, and sales are basically here. So they don't give us the units, but we can assume it's dollars. And they just want us to calculate the mean. If I'm going to write it out all fancy like, and I do recommend you start doing this because we get into some pretty heavy-duty formulas throughout our course. So we're going to start with I starting at 1. Now there's 1, 2, 3, 4, 5 data points, so n is 5. I like to write n is 5 over here. And in no particular order, it's going to say, all right, add them up. Literally, if you want to, you can write them all out. What I'm going to do for the purposes of showing my work is I'm going to write the first one, 35.58, and go plus, and then dot, 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 plus, and then write the last one. If you did this on a test, I would consider that enough work so that I know what you're doing. Like, I know you know what you're doing. Like you just said, I'm going to start on the first one, and then you did dot, dot, dot. Like, I'm not going to write them all out. But I know that you know if you do it this way that that's the way that you added them all up. Make sure you get the right number, okay? You do not do well if you calculate something wrong, okay? Businesses live and die on their calculations, right? So it's got to be the right number. So when you add up these 5 numbers, take a moment, grab your calculator, add them up. You should get 129.29 divided by 5. It's going to write X bar again. And when you're done, you get 25.86. So the average of this sample is 25.86. Done! Is every question going to be that easy? The answer is no. But for now, for today, yes. The median. The median is a value such that 50% of all the measurements after having been arranged in numerical order, from least to greatest, we should add in there, lie above or below it. So the median is another way to measure the average. It is different than the average. So the average is where we just add up all the numbers and divide by the number of numbers. The median is when we actually order the numbers from least to greatest. And then we actually look at the exact center. So what is the number in the middle? So that we have the same number of numbers to the left of that number and the same number of numbers to the right of that number. That's the median. Sometimes it's exactly the same as the average or the mean, but sometimes it isn't. We're going to learn a little bit more about the median. I got some fill in the blanks here, so important. You must always arrange the data from, do you remember what I said? From least to greatest. So if I say do the median, you must organize the numbers from least to greatest. Okay? For the average, it doesn't matter. You can add them up in any order, but for the median, you must. Okay, now there is some little stipulations here. If the number of measurements is odd, so as in if you, let's say you have 5 data points, the median will be the middlemost measurement in the ordering, right? If you got 5 data points, so I'm just going to go 1, 2, 3, 4, 5, right? I've ordered them from least to greatest, and check it out. The one in the middle, 3, right, is my median. Why? Because I got 2 numbers to the left of it and 2 numbers to the right of it. Boom. It is the exact center. The word median means center. This is where it gets trickier. The last bullet here. If the number of measurements is even, then you're in for a bit of pain because the median is going to be the average of the 2 middlemost measurements in the ordering. Why? Let's add another number here, 6. Well, check it out. I now have 6 data points. Where is the middle? The middle is right here, somewhere in between 3 and 4, right? So visually, if I were to average the middle 2 numbers, now I have two numbers to the left and 2 numbers to the right. So the median in this case would be 3 plus 4 divided by 2, or 3.5. All right. Here we go. Let's do an example. Boom, boom, boom. Oh boy. I need to get a stylus. It's tricky to write. So, the average annual amounts of people in Canada spent on rent between 1997 and 2005. Remember 2005? So it's 9 years. Here's the yearly rent, I hope. Those are some swanky apartments at $8,553. So we got them all here in no particular order. And, well, there we go. There's the answer. The median is 7,523. I put it there so you can see the answer, but the important thing is how do we get there? So first thing is we need to arrange these numbers from low to high, right? So, you scan through, find the lowest one. It's this one. So 6606. And what's the next one? This one. 6806. And what's the next one? Ah, there it is. 7043. I'm focusing so hard because I want to try to make sure that I can write it all on one line. There's the next one. And there's the next one. 7523. And then we got 7873. I'm getting bad at crossing them off. Oh, it's not going to happen. No, not going to happen. Not going to be able to write them all in one line, which is really annoying. I might be able to if I switch colors here. So I got the 8200 one, and now I'm going to go 8, 5. There we go. And then last one, 88, 5, 6. And I cannot make an 8 with my finger very easily. I promise I'll get a stylus for the next video. So there it all is, laid out from least to greatest. I suggest you double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 pieces of data. Check and make sure you have 9 and that they are actually least to greatest. The biggest mistakes you see on these questions are transcription errors, like you write a digit wrong, and I'm just going to tell you, don't do it. Okay, like you will lose marks for doing stuff like that. Okay, you're doing statistics and you're supposed to be precise. Okay, so will you get 0 on the question? No, but does it hurt to lose half a mark or a mark on an easy 3-mark question? Ugh, it does. Okay, so don't do it. So here we go. Least to greatest, we're done. Now, we have, well, I've said it 100 times, but I haven't written it down yet. We have 9 pieces of data. So it's an odd grouping. Okay? If it's an odd number of numbers, the median will be in the middle. Now, some of you will sort of visually see it, and that's great. But if you're kind of like me and you're not always super visual, is there like a formula we can use to sort of figure out which number would be the middle? And the answer is yes. So to find middle, take your number of numbers, 9, and divide by 2, and that gives you 4.5th number. What's the 4.5th number? You got to round up to the 5th. So according to this, the 5th number, that's an arrow pointing up. The 5th number should be my median. So let's see, 1, 2, 3, 4, 5. There we go. That would be my median. I can check. There are 4 numbers to the left of it and 4 numbers to the right of it, so it must be my median. Yay! Very nice. That is so exciting. Well, I would like to do one more example here and say, what if it was an even number of numbers? Okay, but as I said, you have to do the average there. So let's kind of go part B and say, what about even? So let's add, we'll just arbitrarily add 9,000, right? So we can just tack it on to the end and it's not going to be too hard. I'm going to have to do some erasing here. I don't like doing it, but here we go, because I'm going to need some room. Okay, so make sure you have that written down. I'm going to redo it so that it's even. So add the number 9,000 to the end. I'm going to erase all that. Oh, get out of here. Get out of here. All right, so it's going to kind of tack it in down here. We have the number 9,000. So now we have 10 data points, so n is 10. Find the middle. So the middle is 10 divided by 2, and that's the 5th data point, right? But remember, the 5th one, which is the one that we've circled, is not the true middle. You got 4 numbers to the left, and you got 1, 2, 3, 4, 5 to the right. So we're going to have to actually average the middle too. Average them. So we're going to take 7,523 and add it to 7,873. There's 2 numbers. Divide by 2. So I keep forgetting to write MD for middle. So I'm very bad. Sorry about that. And when you do that, you should get 7,698. There. So when it's an even data set, your median is not actually part of the data set because you're going to calculate it. If it's an odd data set, the median is part of the data set. Wow! All right. The mode. What is the mode? It's another measure of central tendency, and it is simply the measurement that appears the most frequently. Okay? And that would be sometimes considered some sort of average. Doesn't work very well in very, very small data sets, but sometimes if you have really, really large data sets, sometimes, depending on what the data is, you actually get certain numbers that pop up a lot. Okay? So it's not used very often. It's more like a definition kind of thing that comes up in our class. Like, it's basically a freebie. You know, that first test is going to have some question on there. What's the mode of this data set? 1 mark, easy mark. Count up the number that comes up most often. There can be more than one mode. Okay, so if you got 2 numbers that are in a tie, you got, say, 2 7s and 2 9s, then, you know, the mode is 7 and 9. There can be 3 modes. There can be 100 modes, okay? I won't give you something like that. I'll give you a small data set, okay? This is important. When the data is in classes, so like when you're making a histogram, the tallest box is considered the mode. Little tidbit for you there. All right, so we got a question here. I thought it would be good to, you know what, I'm going to do this in a separate video as just a quick, like, here is mean, median, mode. So I'm going to skip this one. If you want to see it, I will put, I guess, a link in the description to, you know, extra practice questions or something like that, guided practice. So I'm going to skip this one, and I'm going to go to comparing mean, median, and mode. So we were talking about the 3 different shapes. For a bell-shaped distribution, it means that the mean and the median and the mode are all the same. So if you look at our symmetrical bell shape, right there in the center of the distribution is the average, right, is the mean, median, and mode. If you have a positively skewed or right-tailed distribution, the mean is greater than the median, which is greater than the mode. So if you look down here, there's the symbol for mean, right? Remember, the population mean is a little u. Okay, so that's what makes something right-tailed. Now, if you have a left-tailed distribution, then you'll see that your population average is the smallest of the 3 different averages. Now, am I going to pull this out in a test? Probably not. Probably not. But it is good to know this stuff. Here we are, percentiles and quartiles. So what are they? Well, say you got a set of measurements, and you have them arranged in our favorite order, which is increasing order. The pth percentile is a value such that p% of the measurements fall at or below the value. and that when you go 100 minus p, percent of the measurements fall at or above the value. Wow. What the heck does that mean? Well, look, when you have a percentile or a quartile, you might hear something like, hey, you're in the 99th percent. That's amazing. That means that you do better than 99% of people in a certain category. So that means that if you're in the 99th percentile, 1% of people do better than you, and the other 99% do worse than you. Okay, so we can break that up into quarters or quartiles. So the first quartile, also called Q1, is the same thing as the 25th percentile. So if you're at the top of Q1, that means that 25% of people are doing worse than you and 75% are doing better. Kind of means you're at sort of the bottom, the middle, the bottom quarter. The second quartile, which is also called the median, right? That's the 50th percentile, right? So if you're exactly in the middle, well, that's the median. The third quartile is the 75th percentile. So if you're in the third quartile, that means that you're doing better than 75% of people and 25% of people are doing... Sorry, I said that right. Yeah, no, I said that right. You're doing better than 75% of people and 25% of people are doing better than you. Now, there's a little definition for something called the IQR. It's called the interquartile range. It is defined as Q3 minus Q1. And it is what it is. It is a measurement that is often of interest. So, know it. And I do have a little blurb to write. Very important here. So, for rounding, if you get a decimal answer, you will always round up. If you get exactly an integer, like 1, 2, 3, you will average that data point and the next one. So that's in the context of figuring out quartiles and percentiles and things like that. So when you're doing these things, just keep in mind that when you're rounding, if you get a decimal answer, you're always going to round up. Okay, if you get exactly an integer, then that means that you're going to average that data point and the next one. And let's see what that means. So here's an example where we're going to find all the quartiles and the median for the following set of data, which are 20 customer satisfaction ratings. Now, we already put them in order from smallest to greatest, which is something that you must do when you're doing quartiles and percentiles and things like that. And how do we do it? Well, here it is, the formula. So say I'm going to find Q1. Well, you are going to be going 1/4 times the number of data. So 1/4 of 20 is your 5th data point. So that's what I mean by you're going to average that data and the next one. Like Q1 is not 5. It is the 5th data point. So if your data is not in order from least to greatest, then you will not be finding Q1. Now, remember, because we got an integer, right? We got exactly 5, then to do Q1, we're going to have to average the 5th and the 6th data point. Okay, so just trying to make this easy here. I'm going to count 1, 2, 3, 4, 5. So it's going to be the 7th and the 8th. That is Q1, whatever the average is. Well, that's fairly easy to do in our heads, right? 7 plus 8. What's in between 7 and 8? 7.5, right? So Q1 is going to be, to show the work, 7 plus 8 divided by 2. So Q1 is equal to 7.5. Perfect. Now, to do the median, we can tackle it one of two ways. We know our definition from before is that it is the exact center of the data set. Right now, we have an even number of data, so it's going to be an average of the two. If I'm using my formula, because it's the median, it's half, right? Because it's 50%, half of 20. It's the 10th. Now I got an integer, so that means 10th and the 11th data. Okay, so let's see if I can do this. Oops, wrong one. So 8 is a 6, so then 7, 8, 9, 10. It's the 2 8s. It is specifically these 2 8s. There, that's the median. Okay, so, well, 8 plus 8 is divided by 2 is still going to be 8. So the median is 8. Perfect. Now, we also need to figure out Q3. So Q3, or the third quartile, is going to be 3/4 times 20, which unfortunately is going to give us, the 15th data point. So because we got an exact integer, we're going to go 15 and 16th. So now I'm not going to do the calculation for this one, but Q3 is those two right there. When you count up, it's a 9 and 9. So when you add them up and divide by 2, you're still going to just get 9. Okay, now I'm running out of room, but up here, over here, I don't know if you guys can see, I'll do it in red. Up here, going to do the interquartile range. So remember, the interquartile range is simply Q3 minus Q1. Okay, so my third quartile is 9, and my first quartile was 7.5. So my interquartile range, or IQR, is 1.5. Now, we will talk about where that gets used, probably in the next example, but there you go. So there's a really easy question for quartiles. Now, visualizing these things, well, there's a thing called the Box and Whiskers Plot. Now, I used to really like cats. No, not so much anymore, but it's called the Box and Whisker Plot because it kind of looks like, the whiskers of a cat. So we'll see that. We'll draw a pretty cat picture. The box portion of the plot plots the first quartile, the median, and the third quartile. Then there's something called the inner fences. Sorry, I thought I had the highlighter. It's atrocious. So the inner fences, and the inner fences, this is where the IQR comes in. So it's just sort of an arbitrary, the inner fences are 1.5 times the IQR away from the quartiles. So you're going to be doing 2 calculations to find the inner fences. You're going to be going Q1 minus 1.5 times the IQR, and then you're also going to figure out what is Q3 plus. So basically you're going to have your data. Right, you'll kind of have your data. It's going to look like this thing, and then we're going to figure out what is the inner fences, and then we go like this. Okay, and you'll have like your data points fallen in here. Okay, so it's kind of like it's a way of beginning to understand where are the outliers. Remember I said how you interpret what an outlier is kind of depends. So one way of doing it is to calculate these inner and outer fences. So the inner fences are just defined as 1.5 times the interquartile range. Okay, you're still within the data set there, but you're starting to get a bit more towards the extremes. Now, the outer fences are 3 times the IQR away from the quartiles. So very similar setup, but you're going 3 times IQR, and you're subtracting it from Q1 to get one outer fence, and then you're adding it to Q3 to get the other side of the fence. Anything beyond that is usually sort of considered an outlier. Okay, now, I don't usually, for simplicity and for making these questions not too long, I don't usually make people calculate the outer fences. Okay, so in the question I do, I'm not going to calculate them. I would like you to know the definition of the outer fence, but I'm not going to get you to do it. We'll always, if I ever ask you to do a box and whisker plot, you're going to be doing Q1, Q3, the median, and then the inner fences. All right. That being said, let's go ahead and do a box and whisker plot. Now, I would like to use the last data set for simplicity. So the one that we just did, I will go back. Memories, here it is. So we got our Q1 popping in at, 7.5. And then we got our median at 8 and Q3 at 9. And then oh no. There we go. An interquartile range of 1.5. It won't let me highlight off my slide, maybe, I suppose. No, it does. Okay, perfect. So, using that data, so write it down, ladies and gentlemen. Whoops, there we go. So, just use last data set. Let's go ahead and make a box and whiskers plot. So you do sort of need like a bit of a number line. So again, use a ruler. I am not. I'm using my finger. Not bad. So, my median was 8. My Q3 is 9. Like, I think I'm just going to go up by ones. So 8, 9, 10, 11, 12, 13, 14, 15, something like that. Now, by no means do you need to have every single value there. Now, I don't quite remember where I was hoping to go. So there we go. Something like that. There. Okay. So I guess a valid question is, would I provide some sort of scale on the test or something? And the answer is yeah. Like usually I give you a number line with increments that are equal, and then you decide like what your scale is going to go up or down by. Okay. All right. So what's this bloody thing going to look like? Well, we are literally going to make a line where Q1 is. Now Q1 was 7.5. And it is very nice to write the number that it's supposed to be above. Whew, I drew that pretty big, but there you go. Okay, then go ahead and draw a line where Q3 is. So right there, and you can even label it Q3 if you like. Now it's right on 9, so there's really no need. And then you connect those. So there's Q1 at 7.5. There's Q3 at 9. Now the median was 8. So you draw another line there, and then you label it median. And then we need to do a little calculation for our interfences. So the interfence. So one of them is Q1 minus 1.5 times the IQR. Okay, now Q1 is 7.5 minus, when you actually do 1.5 times the interquartile range. Now remember, the interquartile range was 1.5, I think. Yes, it was 1.5. So on your calculator, you're going to go 1.5 times 1.5, and you're going to subtract that number from 7.5. Now, 1.5 times 1.5 is 2.25. So when you go 7.5 minus 2.25, you get 5.25. It's going to kind of do that. So go find 5.25 approximately. Yeah. I'm going to label that 5.25. So you just draw a little tick mark, not as big of a line as the other ones, and then you're going to draw a line coming out from the box going to there. So that's one of the whiskers. You can kind of see this is starting to look like whiskers, right? When you do the other fence, which is Q3 plus 1.5 times the interquartile range, well, Q3 was 9. 1.5 times 1.5 was 2.25. When you add it up, you get 11.25. So there's 11, a little bit bigger. Label it, right? If it's not on the scale, label it. There. Now, hopefully yours is way neater than mine, but this is a box and whisker plot, also sometimes referred to as a 5-number summary. Okay, so the important numbers are Q1, the median, Q3, and then the interfences. So there's 2 numbers for the interfences, right? The small one and the big one. There you have it, box and whisker plot. So I could ask you to draw me one of these for a data set. And what does it do? It helps us visualize the data, right? Sometimes you computer programs or whatever will put a bunch of little dots for all the data points. So you can overlay this with every single data point. So then you can visualize, like, you got all your data points. Are they grouping sort of between Q1 and Q3, or are they grouping kind of towards the fences? You can visualize the data that way. I'll never get you to do that, but I will get you to make a box and whisker. And here's some other ways of displaying data that you're probably familiar with, like, horizontal and vertical, charts, pie charts. I'm never going to get you to do any of these, okay, but obviously just want to make sure you're aware of them. There are other ways of displaying data. Scatter plots. We will get into some scatter plots with Excel later. But yeah, you can use it. Actually, we're going to do quite a bit of stuff with scatter plots later on, but not really making them, but figuring out trend lines and things. So that's a very, figuring out trend lines is a big deal. So yeah, use to study relationships between two variables. One variable on the x-axis, other variable on the y-axis. And yeah, we'll get there in weeks. It's quite far out. Now, here is a little example of, it's a scatter plot. I'm never going to get you to do a scatter plot by hand, but you can already start to see that, this data, there seems to be maybe a line of best fit somewhere around there. Eventually, we'll be calculating that and calculating a bunch of other things. That's weeks from now. So just want to throw that out there. Yes, I promised you misleading graphs and charts. Yes, I did. Well, excuse me. One way of doing a misleading thing. I don't know if that's good English, but one way of creating a misleading chart is by having a scale break. So what's the scale break? It's just right here, So 0 supposedly is down there, and just sometimes they'll just use a little kind of broken line thing, and then all of a sudden we're at 58,000. That can make differences seem a lot bigger than they actually are, right? So like the difference between here and here look a lot more drastic when you chop off, right, from 0 to 58,000, right? But if you could see from 0 to 58,000, you'd realize there's only, it looks like a $8,000 difference from the smallest to the biggest. Is that so drastic? It looks pretty drastic. This thing is so small. This one looks, this bar looks almost double, right? But it's only $8,000 more. So, skewing the perception like that can make it look quite dramatic. There's other ways of doing it too. They're all explained here. So B is when the vertical scale starts at 0, the increases in mean salary look less impressive. Yeah, so if you want to minimize something, so make the differences look sort of smaller maybe than they actually are, then zoom all the way out. In A, it's like, don't skip 0, right? Don't do that. But then in this one, it's like, well, if you do it, then things look smaller. But, it's just like, if you want to push a certain narrative or something like that, these are the ways you can do it. So you just need to be aware, right? Like when you look at a graph, you just need to be aware that there's different ways of showing you the data that might affect how you think about the data. Okay. Also, there's two others. I'll let you read about them. Like, well, I guess what are we going to do with this? I just want you to know them. I could certainly throw out like a multiple choice question, like to talk about one or identify one of these. Which one is a misleading practice? Okay, so maybe know them for that reason. So other ways of doing it. So a compression or a stretch can make things look different. So you can read these on your own. I'm not going to read these for you. Read them yourself. And I say that with great respect. Read them yourself. If you have any questions about them, let me know. Check the homework to see what kind of questions you're going to get. Now this is important. Measures of variation. So something called, let's get all the definitions out of the way. So we got range. It's the largest minus the largest measurement minus the smallest measurement. So it's kind of like, there it is. That's the range. Largest minus smallest. That's called the range. The variance and the standard deviation are very important. Okay, so we're going to talk a lot about variance and standard deviation, and it's kind of hard to really understand them without doing some calculations, but let's try. So the variance is the this is going to be a mouthful here. So the variance is the average of the squared deviations of all the population measurements from the population mean, mu. What the heck does that mean? Look, basically, you have your mean. Say your mean is 5. And then you have some other data points, like you got a 6 and a 7, and you got a 3 and a 4. Okay? If you calculate the difference of every data point from the mean, okay, so you got your mean of 5. Say you got data point 3. Well, what's the difference between 5 and 3? It's 2. Okay? And then you square it. Why do we square it? We can get in that later, but there's lots of reasons, but you square it. Then you do the next data point. So I said there was a 4, right? So the difference between 4 and 5 is 1. Okay, so if you add them all up and average them, you get the average deviation squared. That's the variance. What the heck does it tell us? It tells us lots of things, but in general, it can give you an idea of, on average, how spread out is the data from the mean. So if the mean is 5 and you have like a variance of like 1.1, then you sort of have an idea of how spread out, so how far away on average is every data point from that mean. Okay, what's the standard deviation? Well, it's the square root of the variance. Okay, and the standard deviation is usually the number we look at. So because you might have been like, why are we squaring the difference? Well, the truth is we usually look at the standard deviation. Okay, so standard deviation is basically, what is the average deviation from the mean? Okay, so if I was to write something out there, it's the average deviation from the mean. That's it. That's a very... It's not the best way to think of it, but it gives you a pretty good understanding when it's hard to visualize what it means. Okay? All right. So what does this mean for us? Well, for us, it means that we're going to start calculating this stuff and prepare yourself for formulas. So boom. Woo, it looks ugly. This is the formula for variance. It is not very nice. There's the formula in the compact form. Now, again, you have formula sheet. It'll be on there, but it doesn't do you much if you don't know how to use it. So we have that E-looking symbol again. Remember, that means the sum. So you're doing the sum. I'll use maybe red. Well, let's use purple. You're doing... Ooh, that's very thin. Sorry. A little bit better. Still very thin. I actually set it to that without really checking. All right. There. So you are doing the sum of every xi. So that means every data point minus the mean squared. So you're going to take every data point, subtract the mean, square it, write it down. Take the next data point, subtract the mean, square it, write it down. And when you have all those numbers, you're going to add them all up, and then you're going to divide by the total number of numbers n. So what follows is just the expanded form of the formula, right? So it's like take your first data point, subtract the mean, square it. Take your second data point, subtract the mean, square it. So on and so forth until you get to xn, the last data point, and then you add it all up and you divide by it. Now, what's up with this second formula? This one here. It says for sample size n. Well, remember, the population is when you are talking about everybody. So everybody in the NBA, right? That's the population. Oftentimes in statistics, statistics is sort of the art of figuring out what the population is by taking a sample. Okay? So, and we make distinctions in the formula. So it's exactly the same formula, but instead of the symbol here, which I didn't even talk about, so this is the symbol for variance. It's sigma. It's another Greek letter. That's sigma. And then sigma squared means variance. Sigma without the squared is the standard deviation. So if it's a sample, then we use S. Okay, S for sigma. So this is sample. This is population. Later on, as we get deeper into the course, we are always very concerned about whether or not a number is the population number or the sample number. Okay, but yeah, same formula. You'll notice that if it's a sample, we use x bar. If it's a population, we use mu. But both of these things mean average. Just one is the population average, sometimes called the true average. And the other one, x bar, means is the sample. So it's just a symbol that mathematicians use so that they know, looking at just the formula, are we talking a sample or are we talking the population? So population standard deviation is when you do the variance, the square root of it. That's your standard deviation. If you're doing a sample standard deviation, then we simply use S instead of sigma. Hooray! Let's do a freaking question. Oh boy, I hate going over all the terms. All right, but it is important because we do have to know them as we're going to use that lingo a lot. All right, finding standard deviation. So a sample is collected from CEOs and the number of cats they have. Weird. 42586. Find the standard deviation. Well, it doesn't get any easier than this. I'm not saying it's easy, but this is about as easy and straightforward as a question like this can get. So looking at my standard deviation formula, and obviously this is a sample, right? So when I write it out, Because it's a sample, I very much expect you to write out the correct formula. It's usually a good first step. So it's the sum of every xi minus x bar squared divided by n. And I starts at 1, and we have 5 data points, right? So n is 5. So that would be right here how you would write out the formula. So this tells me that you've clued in on what it is. And you're going to be noticing here, right? Well, hey, to do this formula, we need to know the average. Well, we were talking about averages this lecture. So we can go ahead and find x bar. It would just be adding up all the numbers, right? So adding up all the numbers and dividing by 5. Never do that, actually. Always go to the next line. So never just keep writing equals. That's a very bad habit. I do it to save space, but never do it. So I'm going to try to not do it. So when you add them up, you'll get 25 divided by 5, or 5. So the average number of cats these CEOs have in this sample are 5. That's way too many cats. So, well, if you were going to write out your work, which I don't want to give you the impression that it's optional. You need to write out some work, okay? Write out the formula, write out some work. So in this question, because it's an example, I'm going to write out every single one. And I would say that you should too. I'm going to go down here. Let's write s squared equals. So we're going to take each data point, xi, and subtract the mean and then square it. Then we're going to divide the whole thing by n. Now, I think I might have actually missed something here. This is my mistake. I didn't point it out. For a sample, you'll notice that there's a difference in the formula, right? It's n minus 1 for a sample, and it's just n for a population. Now, it's a big ordeal. Basically, n minus 1 is just a correction factor. Okay, so we go n minus 1. Okay, if it's a sample, we make our n a little bit smaller than it actually is, realizing that the sample might be off. It's a very easy explanation for that. All right, so I'm going to take my first data point, 4, and subtract, what's the mean? 5, square it, and then add it to the next one, which is 2, subtract the mean, square it, plus the next one, 5, subtract the mean, square it, plus 8, subtract the mean, square it, and can I squeeze it in, plus 6, subtract the mean, square it. Great. All divided by 5 minus 1. Okay, now I recommend you pause the video, figure out those numbers for yourself, and I'm going to write them. So the first bracket gives us 1, the next bracket gives us 9, and then we get a 0, and then we get a 9, and then we get a 1 divided by 4. So I'm running out of room, so I'm just going to draw an arrow like that. So you're going to get 20 divided by 4, which is 5. This is the variance. To get the standard deviation, you do the square root of the variance. So the square root of 5 is 2.24. There. So you might have to replay that. I'm not sure, but that's how you find the standard deviation. I'm never going to give you like a bazillion numbers, right? But I could easily give you anywhere between 5 and 10 numbers and say, find the standard deviation of this data set. Okay? Very important that you show the work. No work, no marks. Okay? So if you get the answer right, perfectly great. But boy, if you make a mistake and you don't have any work, how can I give you any marks? So it's very important that you detail your work so that I can find your mistake and be like, it's just a calculation mistake, and just, deduct half a mark or something. Okay. So also don't make calculation mistakes. I'm not going to be giving you crazy numbers. You have a calculator, but yeah. Oh, there you have it. So this is very important. We'll talk more and more and more about this all the time. But the empirical rule of normal population. So you probably may have heard of this in some capacity. Maybe, I don't know how nerdy you are, but if a population has a mean of m and a standard deviation of s and is described by a normal curve, basically a bell curve, then this is basically the definition of what makes a bell curve a bell curve. The first point. 68% of the population measurements lie within 1 standard deviation of the mean. So we calculated the standard deviation of this. What does this mean? It means 2.24 cats is the standard deviation. So the average is 5. So your average CEO in our sample has 5 cats. But the average difference between all the data points was 2.24 cats. So that means that you can expect maybe a CEO to have anywhere between 5 minus 2 and 5 plus 2 cats, roughly. If it's a normal distribution, you would expect to capture 68% of CEOs would have between 3 and 7 cats, just to use our example. If you go 2 standard deviations out from the mean, so if you add 2 standard deviations to the mean and you subtract 2 standard deviations from the mean, and you now have a range, if it's a normal population, or a bell curve, you have 95% of the data captured there. If you go 3 standard deviations out, then you capture 99%. Okay? So sometimes this is referred to as the 68, 95, 99 rule. So 68% of the data within 1 standard deviation plus or minus, 95% within 2 standard deviations plus or minus, and then almost all the data when you go out to 3 standard deviations. Very important, comes up again and again and again in this course. Lots of formulas are based around this, and there's also formulas that aren't, okay? So what does it mean for us? Well, here we have a very big example. It's sort of a big question that threads a bunch of this stuff together. It does come up on tests. It's a good test question. So the example is the empirical rule. Is this data normal? So we have a data table, and unfortunately there are 49 pieces of data, but they've given us some numbers here. Okay, so I would never give you 49 pieces of data and then say find the average, but they give us the sample standard deviation. Notice how it's a little less. So given a sample standard deviation of 0.7992 and the sample mean of 31.5531, are the prices of these kitty litters normally distributed? Now remember, normal distribution just means a bell curve. Okay, so here it is, all the data, and how would we check it? Well, we just learned that if it's a normal distribution, 68% of the data is within plus or minus 1 standard deviation, 95 is within 2 standard deviations, and 99 is within 3. So if this data set is normally distributed, then we should be able to calculate those ranges and make sure that that the data falls into those categories. So let's do it. So step 1, we're basically going to check 68% within, how am I going to write this? X bar plus or minus S. At any point, if you find that, that's not happening, like when we count this up, if we get 80% of the data falls within this category, then we can say, no, this is not normally distributed. Okay, but you're going to do 3 checks. You're going to check 68, then you check 95, then you check 99. So we need to calculate what is X bar plus the standard deviation here. So let's see, X bar plus the standard deviation. Well, remember, they gave these numbers in the question. So X bar is 31.5531. The standard deviation is 0.7992. So pause for a moment and go and add those 2 numbers up. Now you're going to get 32.4. Now I rounded to 1 decimal because if you look at your data, they're all rounded to 1 decimal. Now go X bar minus S. And if you do that, so if you go 31.5531 and subtract the standard deviation, you get 30.8. Now here's the tedious bit. You got to go and actually count, and I recommend crossing them off or highlighting them, how many data fall within that range. So 30.8 to 32.4 inclusive, how many pieces of data fall in that range? Well, you can pause I recommend you pause and you count it up yourself. Okay. I will highlight if you wish to stay with me. So all of those fall in there. This one. And that one. And this one. 30. No. And this one does 30.8. Ooh, right on the level there. That one. The good news is that mostly, yeah, that one's going to fit. That one. Most of them are going to fall into this category. That already seems to be happening. So look at this, like everything on this line except for one. And this one, that one, no. These ones, yes. Would I do this to you? Like give you this many pieces of data on a test? Yes. Because I gave you, the mean and the standard deviation, there's no concerns about taking a bunch of time calculating those. So yeah, this could totally happen. There we go. So when you count them all up, it actually turns out that there are 33 out of the 49, okay, fall in that range. So that is 67.3%. So does it need to be exactly 68? No, it needs to be pretty close. So 67, 68, 69, that range, yes. So far this looks to be normally distributed. So if that's good, you can go ahead and check step 2. I should mention that I'm not sure if it matters, but I know that when I did my work, I did round my X bar to 31.6. And I rounded my standard deviation to 0.8, just for simplicity. It shouldn't make a difference because you're rounding your numbers anyway, but that is how I calculated my numbers, just in case you get ones that are slightly different than mine, but you shouldn't. But that is the numbers I use. I should have said that before. But so, okay, let's go X bar plus 2 standard deviations. When you do that, feel free to pause, but you get 33.2. When you go X bar minus 2 standard deviations, you're going to get 30. So all we need to know is how many more pieces of data fit now, right? So I'm going to sort of go ahead and, circle these ones. So that's going to fit now. That's going to fit. That one. Remember, we're basically expecting, all these ones are going to fit. That one. Ooh, 33.3 is just out. That one, this one, this one. 29.8 is just out. There. So how many more do we have? If you count them up, it's 14 more. Okay, so we had 33. Now we added 14 more. So now we have 47 out of the 49 fitting. When you calculate that out, you get 95.9%. So that is, remember, it's the 68, right? What's the next one? 68, 95. So a little bit over, still normal. 3. So now we can calculate X bar plus 3 standard deviations and X bar minus 3 standard deviations. So go ahead, do it. Check back. So now that brings us to 34 and 29.2. Now, that literally captures the last 2 pieces of data. So this is 49 out of the 49, or 100%. Now, is that 99 exactly? No, but it's pretty dang close. So what we would say is the data is normal because it follows the 68, 95, 99 rule. You have to have that concluding statement. I ran out of room, but make sure you're right. This data set is normal because it follows the 68, 95, 99% rule. You can't make that claim without showing me the work. Okay, so showing me your calculations as we did here. So don't just guess. And I guess the other question people might have is like, well, how finicky are you going to get? Like, what if I got 64% or something like that instead of 68 in the first question, right? The answer is, there's perfectly normal, right? And then there's really, really close that it essentially is a normal distribution. So I can promise you this. It will be very obvious if it's not normal. Okay, so instead of getting 68%, like you're going to get like 60 or 50, you're going to get like 90, right? Okay, it's going to be very obvious that it's going to be very far away from 68. I promise you that. All right. Ooh. we're going to start moving into z-scores. Now, we're going to be doing a lot more with these later. Here's the formula for it, and then we'll talk sort of about what it means. So, the normal distribution and z-score. So we know what a normal distribution is now. What is a z-score? So for any x in a population or sample, when I say for any x, I just mean for any data point. Okay, so for any x in a population or sample, the associated z-score is, voila, it's x, as in the data point, minus the mean divided by the standard deviation. So what is this? Well, the z-score is the number of standard deviations that x is from the mean, right? You're kind of calculating the average, right? So you're taking your data point, you're subtracting your mean, right? So you're finding how far away is it from the mean, and then you're dividing by the standard deviation. So that's going to tell you how many standard deviations fit inside that number. So if you get a positive z-score, that means that your data point x is greater than the mean, right? Like if I had 10 minus 9, right, then that means, hey, my data point's bigger, so I'm so many standard deviations above the mean. A negative z-score means that you're below the mean. It's a straightforward enough concept to understand. So you have a population, you grab a data point out of it, you already know the mean and standard deviation of the population. Okay, you go the data point minus the mean, which gives you a number, gives you how far away are you from the mean? If it's positive, you're above the mean. If it's negative, you're below the mean. And then you find out how many times does a standard deviation fit inside that number. So your z-score tells you how many standard deviations you are from the mean. Well, we'll be doing a lot with that in the future. For now, I just want you to get used to this idea of a z-score. Okay? So we'll calculate it using our formula. So on this slide, I have a question. I rewrote the formula here. Again, you have it on your formula sheet. What do we got? Population of revenues in billions of dollars for 5 of the biggest Canadian companies. So 38 billion, 37 billion, et cetera, and they have gone ahead and given us the mean, and they've given us the standard deviation here. So we're just calculating the z-score. So let's do it, and then talk about what it means. So for a company that has 38 billion in revenue, here's the calculation, right? So it's x, which is 38, minus the mean, 35.8, divided by the standard deviation. So you get 1.375. Try it out. Pause me, try it out. You should get 1.375. So this is the z-score. So what does it mean? Well, it means that if, in this sample, if your company is making 38 billion, you are 1.375 standard deviations above the average. Okay, so it just quickly tells us, that you're doing pretty good, right? Remember, if it's a normal distribution, 1 standard deviation above the average means that you're already doing better than 68%, right? That rule, 68, 95, 99. So it just gives you an idea of where it's landing in that data set. All right, let's do it. What if your revenue is 37 billion? Well, go Z equals 37 minus 35.8, the mean, divided by the standard deviation. I've given myself 0 room to write. That's okay. Z equals, should get 0.75. Now, you're going to need to write this in on your notes. I'm not going to struggle with my computer to do this. What does it mean if your z-score is 0.75? Well, it means that the revenue of this company at $37 billion is 0.75 standard deviations above the mean. That's it. It's not that complicated. We will do complicated things with this later, but not today. That's the good news. Today we're just getting, this weird concept. Okay, it is a weird concept, so recommend that you got to do the homework. Okay, and got to ask questions. Got to tell yourself, what does this mean? Let's do another one. I'll write out the work for this one. So x is 36. The mean is 38.5 divided by 1.6. What do you get? Z equals, I got 0.125. So what does it mean? It means that this company has makes enough money that they are 0.125 standard deviations above the mean. I'm sorry, I know my writing is getting atrocious. I've been filming for a while, and yeah, I will get a stylus. I promise you this. Now, let's try 34. Now, when you write out this calculation, 34 minus 35.8, it's clear that we're going to get a negative z-score, right? So all that does for us, now go ahead, figure it out. You get negative 1.125. What does it mean if it's negative? It means that this company at 34 billion is 1.125 standard deviations below the mean. So the negative just means it's below. And that's enough for now. Okay? So you have learned a ton today. And there's still a bit more. The good news is I don't generally do a lot of questions on this. Like I think it might be in the homework. It's not going to show up or anything on a test. Well, it might. I shouldn't lie. It might. I will warn you if it does, because it's a bit more obscure. There's certain concepts that we really focus on, and then others that I tell you about, and I'm kind of like, I'm telling you because it's on the course outline, and maybe you might need it later on, like in your career, but whatever. So what is the coefficient of variation? Measures the size of the standard deviation relative to the mean. So there's just a formula for it. It is on your formula sheet. So you go with your standard deviation divided by the mean times 100 will give you the coefficient of variation. So you can use it to compare relative variabilities of values about the mean. Yeah, and business is sometimes used to measure the risk. So let me think here for a second. The bigger it is, yeah. The bigger it is, the usually, it depends on what it is, usually greater risk. Yeah. So, and then what is the risk is going to be highly dependent on what are the numbers about. Okay. So compare relative variability of populations or samples with different means and different standard deviations. Yeah. It'll also let you compare different data sets. You can figure out the coefficient of variation. So you can look at two completely different data sets and compare, this one calculation to get an idea of how similar or how different these populations are. So just a couple last little things. I know I said we're done, but just a couple more things. So what do we got here? I'm not sure that was like an impression of my mom, by the way. So it's like, what is that voice? So if we're talking about a proportion is when you go, there's 10 people in the room. How many of you have traveled to Europe, and 8 people put up their hand? 8 divided by 10 is the proportion of people who travel to Europe, right? So it's a percentage. For population, we use a P that looks like that. It's actually a Greek one, but it basically looks like a P. So that's the population proportion. For a sample, we use P hat. Yes, you heard me right. P hat. It's not a joke. So this is a little angle thing. We'll do a bigger one. So it's a P with a little sort of angle bracket on top of it. That's called P hat. And yeah, it kind of looks like a hat, so it's called P hat. I'm not kidding you. This is how you do a sample proportion. Now, I usually don't do a question on this. I have a question, and I suppose I'll do it. But I don't do it because a proportion means you're calculating a percentage, right? You know how to do that. But in case you need a refresher, here's a marketing ethics case question. 117 out of 205 marketing researchers disapproved of an action taken in a hypothetical scenario. So make an inference about the population of marketing researchers, of X, the ones who disapprove, versus N, the total surveyed. So this is the sample. You're just going to go P hat, right? And remember, the formula is it's just the sum of all the xi's, right? Starting on a 1 going up to n divided by n. So in this case, how many people disagreed? 117 divided by 225 to find 0.57. So I think it's important to see this because it's a very straightforward question, but when you start looking at formulas like this and all the lingo, it can kind of get confusing, but it's just a proportion. So there you have it. Now, very important. Chapter summary. I mean, how do you summarize what we did in 4 bullets? But there it is. So you can read through those if you like. Probably, this is a really good one, like the summary of what a z-score is. So a z-score tells us how many standard deviations a given data point is from the population mean. Okay, z-scores will become very important later in the course, so I'm introducing them very early. We looked at, how to compute descriptive statistics, so mean, standard deviation, a lot of stuff there. And then we looked at a lot of, graphing, stem and leaf plots, histograms. We looked at, misleading things. And then we also compared central tendency. So that was Q1, median, Q3, mean, mode, all those things. Yeah, I get that's actually a pretty dang good chapter summary. Wow, I'm impressed with myself. So homework and exercise as well. Yeah, this actually doesn't apply. Got rid of that for this year, so that doesn't apply. Yeah, the Moodle page. Email me if you need help. But I've emailed out the Moodle password. There's the problem set that we're going to be doing in class, so we're connecting later. We're going to be doing a couple of problems together. Not problem set on Connect. It's more like Moodle. So I suggest some questions to try out. Now, if you have the textbook, you can go get them. Otherwise, I actually have everything there. So just it's the specific questions. Later on in the course, so in a few weeks, I've developed detailed answer keys for everything, because some questions are very involved. For this, I think it might just be the answer to each question. That's actually a lie. I have a semi-detailed answer key. So good news is I'm recommending for you the minimum number of questions and exactly which ones you should try. You have to do them. If you don't do them, this is a university class, and I apologize if you're not in your first year, but if you're first year, sometimes it's unclear how much you need to study. You need to review the notes that we've done, literally rewrite them, redo them without looking a couple times, and then you need to try these homework questions. Okay, you might have to do them several times. Email me if you need help. I am available by email. I'm happy to pop on to Zoom as well if we can find a mutually agreeable time. And, with all that being said, you guys have been great. And I will chat with you when I chat with you. Bye-bye.